This video is going to look at how to calculate expected values for a Poisson sample to be used in a chi-squared goodness of fit test. And we're going to use the TI Nspire calculator to find those expected values. So I talked about expected value of a distribution in a previous video about how to find binomial expected values. So just to reiterate, expected value of a distribution is different than expected values of a sample. If you have a normal distribution, the expected value is the parameter mu, the mean. If you have a Poisson distribution, the expected value is the parameter lambda, which is the mean as well as the variance. If you have a binomial distribution, the expected value is n times the probability of success. The expected values or frequencies of a sample will be n times p. It's your sample size times the probability of each and every outcome. And so you would do this calculation over and over again for every single possible outcome. That means if you have a whole bunch of outcomes possible, you'd have a lot of calculations to do, which is annoying. And that's where it's beneficial to use the spreadsheet feature in your TI Nspire. So let's look at a Poisson example following with those tulip problems that I did in the binomial video. You've now planted your tulips. Historically, your patio had only about 3 bumblebees visit per day. Now that you've planted the tulips, you want to see if that frequency has changed. As you sit and enjoy your daily afternoon tea, hypothetically, always at the same time every afternoon, you count how many bees you observe during that hour each day, and you do this for 30 whole days. Let X be the number of bees that you see in an hour each day recorded. So this is Poisson because we're looking at number of somethings happening per day, and we're assuming that the bees, the number of bees that visit each day are independent of the bees visiting the day before. So they're all independent from each other. Our null hypothesis is that our sample, our 30-day sample, comes from a population where there's, maybe you think that you're only going to have 3 bees per day in that afternoon tea hour. The alternate is that the sample does not come from this population, that maybe you're getting more bees, which means that this parameter might be different. Maybe it's higher because the bees are loving the flowers. Maybe this parameter is lower because the bees do not like tulips, or your neighbor has more bees. I don't know. Okay, so the sample size was 30 days. In your 30-day sample, you observed the following frequencies. Oh, that should say for bees visiting. And so what this says is that on one day, you got no bees at all. On 2 days, you got exactly 1 bee. On 3 days, you got exactly 2 bees. See what's happening? And you went all the way up. And for 30 days, so if you totaled up this entire row, you'd get 30 days total. Each day falls into some kind of category. And this last category is getting more than 10 bees. So if you're doing a chi-squared goodness of fit test, you'd have to compare these observed values to what you would expect to get if this is following a Poisson distribution with an average rate of 3 bees per day. Okay, so to get your expected values, expected frequencies, you would take number of days in your sample, that's 30, and then you'd have to, in every single cell, multiply it by the probability of getting each of these outcomes. So no bees, this would be 30 days times the probability of getting exactly 1 bee. So there's all these binomial PDFs. This is I said binomial. There's all these Poisson PDFs for every single one of these expected frequencies. And then at the very end, you see how this is inequality, you'd have to have 30 days times Poisson CDF. So this last one is going to be different. Since there's so many, let's use a spreadsheet to calculate all this stuff for us, and then we'll have to do this one a little bit separately. I'll show you how. So here's our plan for the spreadsheet. Let me move this down a bit. In a calculator spreadsheet, our plan is in column A to input your X values. So these are the possible outcomes. So I should have actually like 0 should be my first one. No B's occurring, 1 B coming, 2 B's coming, all the way up to 10 B's coming. We're then going to use our calculator to find every single one of these Poisson PDFs right here. And we're not going to enter the greater than 10. Not yet. Not yet. That's where the Poisson distribution's weird. We are then going to enter all of our observed values, which are these numbers that would be given to you in a problem, and those would go into column C. In column D, we are then going to calculate the expected frequencies. And we'll do that by taking column B's values, multiplying it by your sample size, which was 30 days, and get all those values for the Poisson PDFs. The last row, however, is going to be that it has to represent that greater than 10. And so you're going to leave all of this blank. You're going to enter in your greater than 10 frequencies observed here, and then we're going to calculate the greater than 10 frequencies using a Poisson CDF for x greater than 10. Multiply that by the number of days. So that's our plan. Let's give it a shot. All right, in your TI Nspire, we're going to open up a new spreadsheet. And the first column are going to be the variable values. So you could just call that X or variable or outcomes. And the second column is where we're going to calculate the probability of those outcomes. So you can call it PX or just P. So you could get no B's per day, 1, 2, 3, 4, 5, 6 B's, 7 B's per day, 8 B's, 9 B's, 10 B's per day. And the last row is greater than 10 B's. We're not going to enter anything here at all. We're going to deal with that later on, okay? Let's get the Poisson PDFs for every single one of these outcomes. So up here where it says equals, we're going to type equals using the button on the calculator next to trig, and you see how it says PX, so I've taken the title, colon equals means I'm defining it. We're now going to go menu, statistics, distributions, and we're going to choose way down at the bottom, Poisson PDF. The null hypothesis lambda, the assumed rate, average rate was 3 B's per day, and now we're going to choose column A or X. See, I could have just typed a letter A in there and that would have worked. Since I've titled this column X, we're using that title. That's where the apostrophe comes from. Hit equal. Then you can see the whole thing here. Hit enter. Voila, there are the probabilities. So the probability of getting exactly 4 B's per day is 16.8%. And again, we want this greater than 10 B's per day to be blank at the moment because this column only represents PDFs. In this column, I'm going to enter my observed frequencies, and then in column D, I'm going to enter my expected frequencies. So what I observed, my afternoon tea, was one day I saw no B's. There were 2 days where I saw 1 B. There were 3 days where I saw 2 B's, 4 days where I saw 3 B's. There were 8 days where I saw 4 B's, and we're going to keep going down the list from the table given in the problem. And it's really good to just carefully double check all your numbers because you don't want to enter the wrong thing. Now here, this row is supposed to represent more than 10. So we are going to enter in the observed frequency. We had 5 bees on more than 10 days. But again, leave these 2 blank and enter that observed one. All right, so now we're ready to find our expected frequencies, where we're going to have to multiply probabilities by the sample size n for every single one of these cells, okay? And we're going to have to go cell by cell, which is a little tedious, but it's better than having to do all these calculations in a separate calculator page, because we ultimately, to do a chi-square goodness of fit test, we need observed and expected frequencies in a spreadsheet to later on do a chi-squared test. So to get the expected frequencies, you're going to, in each cell, you're going to hit equals, and then you can select this cell, see how it popped up, B1, and then we're going to go times by the sample size 30. And so you expect to get 1.49 bees, or excuse me, 1.49 days where you see no bees at all. You got 1 day where you saw no bees a day, but you would expect to get about 1.5. Now remember, expected frequencies are not going to be actual values that you would get, you know, Poisson and binomial, you're going to have discrete values. Expected, though, you're going to have decimals. So you go down the line, we're going to do equals B2 times 30, hit enter, equals, so I'm just going to go super fast here just to enter all this in, but each time you're entering equals 30 times B and then whatever cell number. Okay, for this last one, so these were all binomial PDFs, but this last row represents greater than 10. This is going to be a I keep saying binomial. This is going to be a Poisson CDF because it represents greater than 10 right here. We're going to hit equals 30 times, then we're going to have a Poisson CDF, so we'll go menu, statistics, distributions, go down all the way to the bottom of the list, Poisson CDF. Average rate assumed was 3 bees per day. Lower bound is going to be 11 because we want bigger than 10. Upper bound is any number that's really big compared to your lambda. So I like to just multiply this by 100 or 1,000. So if you got 300 bees per day, that would be a lot compared to your assumed lambda. So that's good enough. Hit enter. So what this is saying, you would expect on about 6.7 days to see 2 bees if your distribution is still holding true. You would expect on 3 days you would get 5 bees, but you actually got 10 days where you saw 5 bees. So now we've got all our observed and expected values. We can go up to an empty cell and perform a chi-squared goodness of fit test. Menu, statistics, stat tests, chi-squared GOF, observed list, I called it OB, expected list was EX. The degrees of freedom are the number of rows in your observed data minus 1. So we had 11 rows, we actually had 12 rows because we had 0 through 10, then we had greater than 10. So we had 12 rows, and degrees of freedom is going to be 12 minus 1. So I'll just put in 11, hit enter, and the probability of my bees following the average rate of 3 bees per day is, wow, super low, equal to 0. The chi-squared test statistic is actually really, really big. You see how big that is? It's so big, that means that the differences between my observed and expected values are so large that what I'm observing does not follow the belief that I would get on average 3 bees per day. So I can throw out my null hypothesis and I can say that my garden, my sample of 30 days demonstrates that my garden does not follow a Poisson distribution with 3 bees per day.